It's recording now. No more questions? Okay. So what we're gonna do today is it's a linear momentum lab. Yeah. Okay. So basically what we do here, okay, let's if we click this link, and then we will have the simulation and begin. So there's the astronaut holding a fire extinguisher. So when we click activate, the fire extinguisher will propel the air in the outer space. So then they will have the opposite for the outer space will have opposite force work on the astronaut, work on the extinguisher first. Then the extinguisher push this astronaut moving. So let's see how it works. So then start acceleration, then go. So then there's two photo gates and shut off. When you shut off, that means the fire extinguisher start propel the air. So then the astronaut will remain constant motion. So let's say if when I shut off the fire extinguisher around this position, the astronaut will remain will pass these two photo gates with a constant speed. It totally depends on so the motion of the astronaut totally depends on when you shut off the fire extinguisher. So here, let's see, okay, click reset. So here there are a few parameters I want you to know. So in this case, there are three variables which you're gonna use, because whenever we say about like variables in physics, if you wanna study for the relationship between each variable and the consequence, what the consequence you wanna get, you always always keep the two. Every time you just change one variable, so you can clearly see the effect that come from this variable. But let's say there are three variables. One is the time the extinguisher was firing, which means the whole acceleration process, the time for the whole acceleration process. And then extinguisher's force, that means the force that extinguisher gave to the outer space. And according to Newton's third law, the outer space will give him same magnitude but opposite directions external force to push this the whole system, so the whole system of astronaut and extinguisher to move to do the acceleration speed process. And another one is Wally. So the Wally is the astronaut's name. So Wally's mass. So it totally up to, like, let's say if Wally is heavier, then maybe if you have a similar external force, the acceleration will be smaller because it really depends on the mass. We know F equal to ma, right? So this is basically this part. You can do the adjust the extinguisher's force and the Wally's mass. And so these two are two photo gates. So basically they can monitor the time when the astronaut passes two photo gates. And the photo gates are 10 meters apart. So you can do like, if you know, let's say 10 milliseconds, so you can know the speed of this astronaut, right? And also the momentum gained. Okay, so this is basically the idea about how it works. So the extinguisher start firing, the astronaut start moving with the acceleration speed, and then we shut off the extinguisher. Then the astronaut will pass these two photo gates with a constant speed. And then we can record all this data and into our final table. So here, and so before we go into this table and we record all the data we need, wanna help you to understand better about this scenario, and we can understand like where Newton's three laws applied here, and and such. Okay. So basically, okay, let's go from the beginning. So we start this URL and click on the center rectangular box. So basically, we start this impulse lab. So the three variables, which is the extinguishers, the time for extinguisher was varying, and the extinguisher's force, and the Wiley's mass. So these are three variables. This is the delta T, Fn, and MV. And follow, okay, begin. So be aware that photogate time is the time for Wiley to travel between the two vertical right lines, which symbolize two photogates. So this is the time you can record here, and they pass this, the astronaut will pass to this photogates. So in this momentum experiment, why should you shut off the flare extinguisher before Wiley reaches the first photogate red line? Which of Newton's three laws of motion are in effect here? So the reason we want to shut off the flare extinguisher is because we want the astronaut to pass this two photogates with a constant speed. So when so can anyone tell me what are the Newton's three laws? Anyone? I mean volunteers.
What? Can you say that again? What's the question?
Sorry, what did you say?
Can you say that again? What? How much the R or what?
What are the Newton's three laws? Remember? The first law.
An
So,
object at rest stays at rest, and an object in motion stays in motion.
right. Second.
The F equals ma with that.
A third.
And for every action, there's an equal and opposite reaction.
Right, that's correct. Thanks, Sophia. So yeah, those are three laws. So which law you think that we're gonna apply here when we shut off the flare extinguisher, the astronauts start moving with a constant speed? So which law is applied here? After shut off the flare extinguisher? First or second? So you can tap one in chat if you think it's first law, tap two in the chat for if you think the second law. Okay. There you guys here. Okay, so this will be, yes, that's right, the first one. Because like why? Because when there's no external force, so then there'll be there's no external force, you don't have acceleration speed, so you will remain your current moving status. So either if you're still, no force pushing you, then you will remain still. If you are moving with a speed, then there's no external force work on you, so you will remain like moving with your like a speed, right? So after we shut off the flare extinguisher, the astronaut will keep move with its speed that already obtained after the flare extinguisher activation. So in this part, the first law is applied. Where is it? Okay. It's applied when they shut off the flare extinguisher, right? And next one, what is the flare extinguisher proportional effort due to Wally's body mass? Each second is grace. So basically, the flare extinguisher proportion force to Wally's body is like pushing, right? So when the flare extinguisher pushes Wally, and Wally start moving. So they're like, this is how they doing to Wally's body mass. So it doesn't change anything to Wally's body mass. But it kind of helps Wally to move, right? And how many different methods of calculation can you use to determine the speed of Wally? So so how do we determine the speed of Wally? Okay, let's write it here. So the first one, so we write here. Oh, text, sorry. Text. Okay, the first one is we can use this photo gates. So because this is photo gates is 10 meters apart, are 10 meters apart. So the photo gates time we can record. So like we can use S equal to VT, V equal to S over T. So here is S, here's T. This is S, here's T. Right? We can use this one to calculate the volley speed. And the second one is so when sorry. So another one is we have the fire extinguisher force. So we know F equal to MA. So we can get an A, right? And then we know A equal to VT. So we can get a V. Because if we know F we know which is a fire extinguisher's force. F. And so we can mass we know, and we can calculate A, and A equal to VT. So the time of extinguisher start firing, the time is recorded here. So it's just, let's see T1. I cannot see T1, but this is T. Okay. And so we can calculate the speed. And the third one is so we have the momentum gain. So when the momentum gain, we know P equal to mv. And if you use momentum gain that divided by the mass, so you have the speed as well, right? So you have total 3 ways. I want you to write down all the 3 ways, but you just use one, the simplest, to calculate the speed, which normally I would use this S equal to VT. So you have S equal to VT. Just remember the time they give you is millisecond. Momentum, yes. Did I say something wrong? Yeah, it's momentum divided by mass. So you have to convert the millisecond to second, which 1 millisecond equal to 10 to the power minus 3 seconds. So you use the 10 divided by the time, so you have the speed. Now you know how to calculate speed. You know 3 ways to do the speed calculation. Okay, so when is valley speed changing during the spree of the fire extinguisher, or when the fire extinguisher is during the spree of fire extinguisher, or when the fire extinguisher is off. So obviously, when Wally changes his speed, the fire extinguisher is on. So that's why he could also have a acceleration to increase his speed, right? And which of Newton's 3 law of motion are applicable at this moment here? So this is the Newton's second law, because when there's an external force work on the object here is body. When the outer space give a opposite way, the same opposite direction of fire extinguisher impulses delta. Then the fire extinguisher, then the astronaut will have will gain acceleration speed, right? So that's what I want to see here. So in the chat, impulse is F times delta T. Yes, that's right. So let's see how we do that. Okay, if you get confused, P equal to Ft. If this is the equation you remember, right? So why I would say that P equal to M equal to times v is because, okay, let's do the equation derivatives. So p equal to v, okay, so here, v equal to at, right? So then we want to, okay, then now I don't want to use v, I want to use a, right? So I basically what I do is, so I put at to replace v. So p equal to mv. V now I use at to represent, and at. So it equals to p equal to, so ma is f. So I can see ma times t. So which is, so ma we know f equal to ma. So like p equal to ft. So this is how you derive it. But either way it works. Doesn't matter which one you want to choose. So this is the derivation about how, why you think that, like, I mean, it both are correct. Okay, so this is the some like appetizers for us to understand all how this, to understand the whole process. Now we're working. Now we're gonna do the table. Like we do the table, we do the graph. This is all the experiments about. So since we, as I mentioned, there are 3 variables. So the f, this is f n e t. This is mass w m w, and the t delta t. So these are 3 variables. So the first one is you keep. So when we do try to study one variable, we keep the other 2 constant. So the first one is we we keep f and mass. So the first extinguishers force and what is mass constant, and we will change different time for extinguishers to fire, right? So then, okay, so okay. So I'm gonna delete all the equations I wrote here, since I will keep. I'm still recording this, and you guys, if you forgot what the equation you should you should look up, you can always go check the recordings on YouTube. So I'm gonna erase this. Okay. So it's much clean. So okay. So if the first one, if you keep these 2 constant, so the mass always 7 kilogram, the kf mat is always 115. It's up to you. You can change, but you have to remain their constant for the first table. And delta t is your variable. So is your variable that only change in one at this time. So you can activate. So so you change 5 different variables, and the t gate, which is this one, and then you do the speed. You calculate speed by 10 divided by this t gate, and also you do ft. So this is the momentum, right? F times delta t. So F times delta t is here. So then, okay, so here, what I want you to do is you capture different time for the extinguisher was varying. Okay, let me show you. So activate. My computer is really slow. Okay, see? Oh, I think I already shut off because it just like has long reaction. You see, if I shut off immediately, the astronaut will remain this slow speed in the outer space because there's no friction. So he will never become a 0 speed. He will always wander in this small speed. Reset. It's very slow, right? Then activate it again. So we get more speed. Shut off. So you see, this is speed much faster. Okay, so you can record the photo gates here, the time, and you can calculate the speed and put it here. And then you time the, you calculate the momentum. So this is for the first one, it's first trial. And then you do the second one, reset, and activate again. maybe before we shut off here, now I want to shut off here. So shut off here. So I get a different speed for sure. The speed you can calculate by record this time and 10 divided by this and put it in a table. So basically you in this before, okay, so here before, so you will find 5 positions from here, let's see, from here to here. 5 different positions, and before it enters to this photoglyphs. If you wanna shut off after the astronaut goes into the photoglyphs, that means the motion in between these 2 photoglyphs are not constant. Like you cannot use s divided by t to calculate the speed. That's why you will lose how to calculate speed. So like just make sure whenever you shut off the astronaut's extinguisher, shut off before the first photoglyphs, and find 5 positions and record the time here, the delta, which is the time that extinguisher was firing. Okay, so this is the first table. After you've done the first table, then you plot a graph of momentum time versus speed. So like I said, F equal to, so P equal to Ft, which is this momentum, right? P also equal to mv. So that means this graph will give you a linear graph. The slope will be m, because we know P equal to mv. So that's v. If you plot P versus v, then the slope will be the mass of Wally. So this is the first graph. And so we will do 3 tables, 3 graphs. Each table gives you 1 graph. So this is the first one is done when we keep F and M constant. So this is done. And the second, we want to compare, we want to keep M and delta T constant and change extinguisher's force. So when we do that, we have to change, before we have to change the extinguisher's force to be the minimum, and we put it here. While we keep Wally's mass always constant, and so we start from 50, and so we're gonna record the fair extinguisher observation time, right? It's very tricky because there's no reference. You don't know, like if I want to stop here. So what I want you to do is just like try your best to record the same time of a fair extinguisher, because this is millisecond. If there's some errors, so you just try to make sure you can get a similar extinguisher speed. Let's say do one more time. Let's say when I do the extinguisher, I reach to here. So how long does it take? Okay, it's 13,000, basically 13 seconds, right? 13 seconds will be when the astronaut from here to here. Okay, so this is 1, you can try to keep here. It's 13 pretty much. And then you increase extinguisher's force. Okay, I have to reset. Okay, 55, maybe a little bit more. Okay, 85 is fine. So it's 13 seconds. We try to record a 13,000 millisecond. Again, activate. Try to keep it 13,000. Oh, it's a little bit longer. So I would recommend you start from the highest force and decrease. Otherwise, if it applies to, let's say, okay, the first one we have a 13 second. Now the maximum is 11 second. So it doesn't, and I'm sure if we increase this one to, okay, we said, increase to the, oops, Okay, so we're gonna start from the highest extinguisher force. So then we can record the time. Then we keep this time in this column, and then we decrease the extinguisher's force. Okay, start. Let's see how long. Okay. Oh, what happened? Did I click twice? Okay. Did I click twice? I think my computer is insane. Shut off. I really don't know. So, but we see here is 6,000 milliseconds earlier, right? So you put a six. So you see the unit here is second. So you put a 6 second here, and then we decrease the force. So 190. Then we try to keep 6,000 milliseconds here. Okay. So here is 6,000. I know it's sometimes you get errors, but it's fine because you really cannot control, especially if you have a computer like mine. It's so slow, and it really, if you there's 1 second you hesitate, then the result will be different. So I wouldn't be very strict about your time, even you try to keep this one constant. Just try to keep this one around 6, or even lower. So you can finish, you change your external force, and you record the T gate from the photo gates here, and write down, you can calculate the speed, and you don't have to do this one. The last column don't have to do that. And then you plot graph of F versus speed of volley and see what kind of graph you can get, and see if you can find any relationships between F and V. And the third one, where you keep F constant and delta T constant, F constant, delta T constant, and you change what is mass. Still, you do the same thing. At this time, you just try to keep delta T constant, F constant, and change from like maybe, so if I go to from, so maybe 35 kilogram is the smallest mass we can use. So we can 35, 40, 45, 50, 55. We can like list all this mass here and record the T gate from here, and calculate the speed by 10 divided by the T gate. Remember, they all seconds. Make sure you convert your unit, and then you don't have to do this one either, and plot your mass versus speed and see what you can get. And compare your graphs to the momentum value. Then that'll be all for the experiment. And then, so what I want you to do is the first one, answer these questions. You don't do anything, just answer these questions. If you forgot how to answer, and you can check the recordings. So basically, we cannot go over everything. And then I want to see 3 tables at least. 3 tables, 3 graphs, and your thoughts. That'll be all. And any questions? I'll take a recording. Sorry, I'll take attendance before. Any questions so far? I'm gonna stop recording.
So usually when we do these tables and graphs, we have questions about